Thank you all for coming. My name is Miles Baker. I'm co-founder, actually, with Mr. Corey Arendt, who's here in the audience with us today, of a small company called Modular Wind Energy. And we've done some pretty interesting things in blades that I'd like to tell you about today. Minute of quick background. This is basically a technology that kind of had its roots in the aerospace world. So both myself and my co-founder Corey spent a long time in aerospace in the United States, looked around at aerospace and said, well, this is an industry that seems to be declining, not such a great place to be. Let's go get in some place where things are really booming and growing. And we jumped out and stepped into the wind business in about 2010. And we had lots of ideas from the aerospace industry that we thought would be great fits in the wind industry. And many of them turned out not to be very applicable. They basically imported the aerospace cost structure into the wind industry, which is an absolute disaster. But there are some nuggets here that are really good and that we think have produced a really interesting technology and an innovation in blades. I will not read the abstract to you other than to say that we're talking here about our approach to optimizing a wind turbine blade for large turbines. And everybody knows that we are going to large turbines and that you run into different kinds of design constraints. Talk a little bit about how we tackle those and the concept or design that we ended up out of this and why we think it's a good one. Outline, a little bit about blade design considerations and why large blades make sense. This will be motherhood and apple pie, as we say in the United States. It'll be very obvious to you, but maybe worth doing a little bit of groundwork there. Talk a little bit about what we see as being the design drivers and challenges for large blades, and specifically how those design drivers and challenges change as you go past about 45 meters into what I call a large blade, which is 50 meters and up. Look critically at what those design drivers and challenges lead to in terms of criteria for setting a new kind of blade design or a new kind of blade technology. And all of this is essentially setting the question, and at the end we'll say what we think the answer is, which is basically the approach that we've taken to design a new modular blade. And obviously the name modular is in the title of the company, so it's no surprise that it will be a blade that's built in sections. And then a brief summary. So, design considerations. I'm sure that many of the people in the audience have different views of the blade design process. There's one graphic that we've used internally to identify those things that are important for wind turbine blade design. I always like to start at the top right at 1 o'clock in geometry. Modeling and design is sort of empty words, but in the geometry area where you define what are the airfoils, what's the twist distribution, thickness distribution, etc. That's the first input that allows you to do some preliminary aerodynamic and loads calculations, go into structural calculations, power generation, and the things on the right-hand side are sort of the physics-based or engineering-based disciplines. On the left-hand side, you have some things that are more, I call them illities, manufacturability, transportability, inspectability, and things like that. So here I outline manufacturing, transportation, and field assembly and installation. And then at the top left there at the 11 o'clock position is optimization, indicating that all of these are in some level of conflict, and you basically have to iterate and come up with the best compromise design in many cases. Now, one of the trends, and this will be absolutely no news to anybody in this audience, but it's still, I think, useful to talk about very briefly, is turbines are getting bigger, rotors are getting bigger, and large blades are an absolute requirement to be competitive in the wind industry, even now, and certainly in the future that gets even more true. The growth trend is a little bit dated, showing the trends from 1980 to 2005, but that trend has absolutely continued up through 2012 and is expected to continue. And we have always said that we're near the boundary, we're near the largest blades that can be made, and we've always managed to push that back and push it back. If anybody had said in 1980 that we would be building 60 and 70 and 75 meter blades, we would have been called absolutely crazy. We've managed to do it, and I think that the technology that we talk about today is another piece of that puzzle to allow us to push it a little bit further economically. The reason that we're going to larger blades is very simple. It's all about money. So a larger turbine and a larger rotor basically gathers more energy from the wind, produces more power, produces more money, which gives you a better return on the investment. So those are the projects that get financed. A couple of specifics, though, on why this is important for project financing and for determining which projects go and which don't. If you do a relatively straightforward economic analysis of a typical project, and it's a notional 100 megawatt project based on 4 different concepts. So basically the 2 types of changes that we look at are changing the size of the turbine, basically the rated power capacity, and change the size of the rotor from sort of a nominal rotor for that power capacity to a little bit bigger rotor for that power capacity. And what you see, my laser pointer works, is that the small turbine with a small rotor, basically 1.5 megawatt machines with a 77 meter rotor, has a net capacity factor of about 31%. And to make a good return on investment, which is sort of arbitrarily defined as 8% internal rate of return, or IRR, requires a PPA price of about $60 per megawatt hour. So basically that's your cost of energy. One way to increase the value of a project or the economics of a project is just to go to, go down here to larger machines. So go from 1.5 megawatt machines to 2.5 megawatt machines. You have fewer machines. You get a little bit higher net capacity factor, 34% as opposed to 31%. Brings your PPA price or your cost of energy down to $53 per megawatt hour. The other axis is on the same 1.5 megawatt machine. If you go to a larger rotor, upsize from 77 to 82, you bring the capacity factor up to 36% and bring the PPA price down to about $55 per megawatt hour. Nice. The best is when you do both. So larger machines with larger rotors are really where the economics make sense. If you go to 2.5 megawatt machines with an upsized rotor, you can get down to $45, $46 per megawatt hour. So a little bit of background on why the industry is doing what it is. And